Hi, this is Ben Zandy. Welcome to AutoTherm Desktop, a robust engineering platform designed to enhance your productivity. AutoTherm is an automated and interactive workspace for mechanical engineers in the thermofluids discipline, offering a user-friendly environment that provides all the necessary tools and resources at your fingertips. This platform can be visualized as a pyramid. At the base, we have the basic tools. These are the foundational prerequisites that have a broader application beyond thermal sciences. These are located on the top menu towards the left. We have units and dimensions, constants and parameters, math tools and resources, material properties tools and resources. In the middle tier, we feature core fundamental thermofluids tools and resources, which include heat transfer, fluid mechanics, and thermodynamics. These can be accessed from the top menu, starting from conservation equations, heat transfer, fluid mechanics content, thermodynamics, and there's a section on numerical methods. Finally, at the top of the pyramid, we present the advanced tools designed for specific applications equipped with specialized features. Access to these tools requires special licensing. So what do we mean by tools and resources? Resources refer to organized content that provides information on a specific topic within a menu item. This content is presented in the form of definitions, equations, tables, and graphs, similar to lecture notes compiled from various references. For instance, let's explore convective heat transfer in channels, which pertains to internal flows. So we go again back to heat transfer. As we said before, these represent chapters in a heat transfer book. So we find convective heat transfer, internal force convection, and then if you go here, we can see various sections that you can jump to. So here we start at the top. The text panel will display sections dedicated to internal force convection. We begin with some definitions at the very top on Reynolds number, mean velocity definition, pressure gradient and friction factor. We can see here for laminar flows, and then we move into turbulent friction factors. Next, we move into thermal considerations, starting with the thermal entry length, definition of mean temperature, fully developed conditions, energy balance or first law of thermodynamics for pipe flow, and then surface conditions and their impact on variation of mean temperature and surface temperature. Next, we move into Nusselt number correlations, starting with laminar flow, fully developed condition, the two well-known Nusselt number values for constant heat flux and constant temperature. Then the entry region, which is very important for laminar flow, and it's also called Grates problem. Here are the correlations. Then we move to turbulent flow, starting with historical formulations, and then modern formulations, which are much more accurate. Then we move into rough walls and modifications that we need to make for that. And at the very end, we talk about the changes that we need to make for flow in non-circular ducts. In summary, these resources function much like a textbook, providing concise and relevant information that enables you to quickly find equations and definitions you need. Now let's discuss the automated tools. These are standalone applications that utilize the basic tools for unit conversions, material property extraction, and various mathematical calculations. As an example, let's use the tool for the same chapter on internal flows. So we go to heat transfer, convective heat transfer, internal flows, and you can see that the tool is located at the bottom. If you click on that, a form will appear offering an automated environment for studying internal force convection. We notice that these tools are not attached to the main program. You can actually move them around, open multiple tools, and place them on different screens if you want to. Now let's talk about the workflow for this particular application. At the very top, the first thing we need to do is to tell it what's the fluid that's flowing in the pipe. You can do that either by selecting the fluid from the fluids library or clicking on enter properties, and you can enter the thermophysical properties manually. Of course, if we choose a fluid from the library, its properties will automatically adjust according to the changes in film temperature. But if we enter the properties manually, they will be treated as constants. The next thing we need to do is provide geometric information. For a circular pipe, that means the diameter and the length. If it's non-circular, you click here, and this form will open up. You choose your cross-section, enter some values, and press OK. And the hydraulic diameter will enter here, and the cross-sectional area will be calculated for later use. Next, we need to provide the flow rate through the pipe. We can either do that by giving the mass flow rate, or the volumetric flow rate at the inlet, or the average velocity at the inlet. And lastly, we need to specify the thermal conditions. That means first we need to provide what's the temperature of the fluid entering the pipe and what are the wall conditions. Of course, you can give all these values in any units you want, and you can request results in any units. As an example, let's say we have water flowing in a 2-inch diameter pipe. So we enter 2, change the unit to inches, and say 8 meters long with a volumetric flow rate of 10 gallons per minute. Let's assume water is going in at 25 degrees C and the surface of the pipe is maintained at 80 degrees Celsius. If you run this, it will do a number of iterations until the properties are all stabilized, and we reach the Reynolds number of 23,730, which indicates turbulent flow fully developed. And all the results are shown over here. Now let's run this again with everything unchanged, except we change the fluid from water to engine oil. If I run it now, the problem is completely different. We see the Reynolds number is now 24, which is very low, indicating laminar flow. And our Nusselt number is 16.8, which is different from the value of 3.66 that we normally associate with the fully developed laminar flow with constant surface temperature. And that's because we are in the thermal entry region, and by default, include thermal entry effects is on. Now, if I go ahead and uncheck this, because I know my flow is already in thermally fully developed region, and rerun the problem, you can see that now we have the Nusselt number of 3.66 and corresponding result. Now I would like to bring your attention to the panels on the right, which contain controls and supporting calculations. In the correlation corner area, you can choose the correlation used for turbulent flow calculation. If you select the rough wall option, you have the opportunity to enter a roughness, and you notice also that the correlation changes to recommended correlation for the rough wall. In the bottom panel, you will find calculated values for the friction factor, the head loss, and pressure drop. The area to the right allows you to choose your preferred method for calculating turbulent flow friction factors. Similar automated tools are available for various topics in heat transfer, fluid mechanics, and thermodynamics. These tools are well positioned and easily identifiable. For example, let's say we are looking for transient conduction tools. So we go to the heat transfer book, the chapter on heat conduction, transient conduction, and we notice the tools are right below every resources in every section. Sometimes tools utilize other tools to automate specific calculations. A good example of that can be found in the turbojet engine tool. So that would be in the thermodynamics, gas cycles, and you notice that we have the turbojet tool here. If you click on that, the tool will open up, allows you to do turbojet calculations. The very first thing we need to enter is the local ambient condition, pressure, and temperature. Let's say we don't know that, but we know the altitude. So if you click on the Use Altitude tool, the fluid mechanic tool will open up for standard conditions at different altitudes. So if I go and enter, say, 30,000 feet, and if I press Update, since this tool is now called from the previous tool, uh, this will result in the tool hiding and entering the pressure and temperature in these text boxes. We hope this provides a clear understanding of the tools and resources available, along with their functionality. Numerous detailed videos featuring solved problems for all the tools will be available soon. Thank you for watching this video.